Hello, everyone. I'm Zhou from Peking University, China. I'm glad to present our paper called PetS, a unified framework for parameter-efficient transformer solving.
As we all know, since the transformer models have been proposed by Google in 2017, we are stepping into a transformers era. Transformers have outperformed traditional LLMs in various natural language processing tasks and even outperformed CNNs on computer vision tasks in recent years. Unlike traditional LLMs, transformers adopt a Pretrain-then-finetune Paradigm. Some big companies first pre-train the transformer models like BERT and GPT with large-scale datasets. The unsupervised pre-training usually lasts for days to months, even trained on TPU or GPU clusters. The pre-trained models with rich task-agnostic knowledge are provided to application developers, who then fine-tune the pre-trained models on their private datasets on GPU servers. The fine-tuned models are finally deployed to cloud or edge servers to process different input queries. With the practical fine-tuning-based workflow, more than 26,000 models for different downstream tasks have been shared online. However, since each task generates a full model copy, when deploying multiple tasks at a server, the storage and the memory footprints increase linearly. Given the huge number of parameters in transformer models, it results in a poor scalability issue in the multitask transformer serving scenarios. To mitigate this problem, using parameter-efficient transformers has become a popular trend. Unlike the full model fine-tuning paradigm, which trains on all the parameters, parameter-efficient fine-tuning adds new trainable modules while keeps the pre-trained weights freezed, or fine-tunes a subset of the pre-trained parameters, or remove a subset of the pre-trained parameters by setting them to 0. These methods can achieve comparable or even higher accuracy than full model fine-tuning, but have much lower storage overhead since we only have to keep a small portion of PET parameters for each task, and the pre-trained model is shared among tasks. However, we notice that it is inefficient to deploy PET models using existing transformer serving frameworks, mainly due to the following challenges. Firstly, the frameworks should support various PETs since the downstream tasks may favor different PET algorithms, and the application developers may usually choose their best PETs for their tasks. Secondly, current GPU-based serving frameworks like turbo transformers and failseek fit into full model copies. One still has to merge the PET parameters into the pre-trained model to generate full model copies, which still incurs huge GPU memory footprint. Thirdly, the queries of different tasks can hardly be batched due to both the model parameter and the algorithm representation differences. How to improve the system throughput is a challenging problem. To tackle these challenges, we first proposed a unified representation of PET algorithms. Take four state-of-the-art PET algorithms as an example. Although they have different algorithm representations, we can use equal transformation to decouple them into shared operations and PET-specific operations. The shared operations compute with different inputs, but using the same pre-trained model weights, so they can easily be batched together, regardless of the invoked tasks of the queries. The task-specific PET operations compute with different PET weights, which cannot be batched together. However, they can still be processed efficiently with light-weighted operators. For example, the decoupled PET parameters of mask BERT and deep pruning usually have high sparsity, which can be processed by sparse kernels. The new trainable modules used by the adapters models require dense operations, but also have limited computation thanks to their bottleneck structure. Based on the unified representation, we present the PETS serving framework to support the management and serving of multiple PET tasks. Here is the overview. To deploy services, users should first register their tasks by providing the tag or pre-trained model, compress the PET parameters and the types of PETs. Then, the Task Manager module or PETS will register the uploaded PET tasks, assign a unique ID for each task, and store their PET parameters to a parameter repository. After task registration, PETS starts serving queries. Each input query carries the unique task ID and the input data. The inputs are processed by the PET inference pipeline, which pre-processes the inputs, schedules the inputs in batches, and computes the batches with a PET inference engine. Here presents the Python-based user interface of PETS. We first create a server and register several PET tasks, and then load the pre-trained model and the PET tasks into the GPU memory. Finally, the server can fetch queries and compute the results. To improve the serving throughput of PETS framework, we propose two optimization strategies to deal with two remaining challenges. First, the input queries usually have variable lengths, and the invoked PET operators are also different. How to split the queries into batches is a challenging problem. We propose a coordinated batch scheduling, which jointly considers the shared operators and the PET operators during batch scheduling. Second, since we can only batch the PET operators of the same task, PET operators of different tasks still execute sequentially. We propose a PET operator scheduling strategy to put them into multiple CUDA streams to improve the throughput further. As illustrated, in real scenarios, the input queries usually have variable sequence lengths. If we batch short queries with long queries, the short ones have to be zero-padded, incurring useless computation. Previous frameworks like turbo transformers pay much attention to solve such a problem. However, for PETS, we have to consider both the shared operations and the task-specific PET operations. Therefore, we propose a new strategy to coordinate these two paths during batching. We first formulate the total latency of a batch. We use alpha NILI to denote the shared model latency when batching n queries with a maximum length of L in the ith batch. Alpha is the performance model of the shared operators. We use a beta model to estimate the latency of PET operators, where PET indexes the PET type of the jth task in the ith batch, and the lowercase n and l denote the number of queries and the maximum length of the queries to the task. Our coordinated batching has two steps. In the first step, we generate mini batches for each task, which only considers the effect of batching PET operators using a profiled beta model. Specifically, we first sort the queries of each task and then split them to mini batches using the beta model and a dynamic programming algorithm. In the second step, we generate macro batches by combining these mini batches among tasks, which only considers the effect of batching the shared operators using a profiled alpha model. We sort the mini batches according to their length, then also adopt a dynamic programming algorithm to find the optimal splitting positions with low time complexity. Please refer to our paper for more detailed descriptions about the algorithms. In addition to the coordinated batch scheduling, PET operators can be executed in parallel to further improve the hardware utilization. To achieve the PET task-level parallelism on a GPU, PET operators in a macro batch can be assigned to multiple CUDA streams. We use the operational intensity of PET operators as the metric and ensure that PET operators with different operational intensity are assigned to different CUDA streams, so that both the GPU memory bandwidth and the computation can be well utilized. We implement PTS with a Python front end to describe shared models and PT task management, and a CBP backend based on the open-source Turbo Transformers framework to perform query scheduling and inference serving. We evaluate PTS on edge, desktop, and server GPU platforms. The edge platform is Jetson TX2, which has 8 GB of shared memory. The desktop platform equips GTX 1080 Ti, which has 11 GB of memory. We use a Tesla V100 GPU with 22 GB of GPU memory as the server platform. We choose BERT-based, BERT-large, and DistilBERT as the shared pre-trained models and adopt 4 aforementioned PT algorithms to generate the PT tasks. We first demonstrate the scalability of PTS by comparing the maximum number of supported tasks with the conventional sequential serving systems, SEQS in short. SEQS loads full model copy for each task, while PTS works on a single shared model. We keep loading tasks and evaluate whether they can process a batch of 22 random queries until out of memory. As we can see, compared to conventional SEQS systems, PTS supports 4 times to 26 times more concurrent tasks, which can substantially save the hardware cost when deploying multiple transformer-based applications. To understand why PTS has outstanding scalability, we also provide the memory footprint of both PTS and SEQS on the desktop platform. As shown in the figures, we plot the consumed GPU memory by both memory width and feature data on the different number of tasks. As we can see in the left figure, adding a new task only consumes less than 5% of additional width compared to loading a full model copy. As a result, the total memory footprints of 64 tasks occupy less than 40% of the total GPU memory. In the right figure, the data footprint of PTS with 16 and 32 tasks are the same, but the 64 tasks consume 3 times more data memory than the 32 tasks. This is because we use NVIDIA's CUB device memory allocator for dynamic data memory management, and the allocated memory device memory is not strictly proportional to the data size, but aligned according to some rounding rules. We then evaluate the serving throughput with fixed size inputs. We prepare different input configurations with variable batch sizes and input lengths. On average, PTS achieves about 1.53 times higher throughput on 1080 Ti and 1.63 times on V100 compared to the single task serving baseline. We notice that PTS fails to achieve meaningful speedup than single task serving on TX2. This is because TX2 only has limited computational resources and therefore can hardly get benefited from the batched inference. We also compared PTS with conventional parallel serving methods, which puts each model into a CUDA stream and runs them in parallel. As we can see, parallel serving has a better performance when the number of tasks is limited, but PTS has the better scalability and can support more concurrent tasks. To better understand the sources of performance improvement over sequential serving, we break down the execution time of both PTS and SEQS on the desktop platform. PTS speeds up the non-PT operators, including the self-attention operations and the shared linear layers, by more than 2 times on BERT-large and more than 3 times on BERT-base, thanks to the batched execution of the shared operations. And the light-weighted PT operators only take up 27% to 41% of the total execution time. As stated before, in real-world multitask serving scenarios, the input queries usually have variable sequence lengths. To simulate real-world cases, we assume the query's length obeys the Gaussian distribution. We set the mean value to 32 and set the standard deviation from 1 to 8. We compare the coordinated bychain with the fixed-site bychain, alpha-only bychain, and the beta-only bychain. The alpha-only bychain only considers the shared operations, while the beta-only bychain only considers the PT operations. As we can see, coordinated bychain is suitable for queries with small variance in query length, while for queries with large variance, the alpha-only bychain is better. This is reasonable since the shared operations take up the majority of execution time. Finally, we evaluate the performance of the multi-stream PET operator scheduling by setting different number of CUDA streams and testing with different input lengths. We find that increasing the number of CUDA streams can improve the serving throughput on long sequence, but has negative effects on short inputs. This is because the execution time is too short for the GPU scheduler to overlap concurrent streams. Currently, PTS is mainly optimized for serving throughput. We did not consider the optimization for latency-critical tasks. We only evaluated 4 representative PET algorithms. To support a new PET algorithm, one should first identify the PET operations of the algorithm, decouple them from the shared operations, and implement a new PET operator if necessary. The model loading and managing APIs should also be extended accordingly. In summary, to realize efficient serving of parameter-efficient transformers, we presented a unified representation for various PET algorithms to help put them into one framework. We then designed a PETS framework for managing and serving of PET tasks. We presented 2 optimization strategies, including a coordinated batch scheduling and a multi-stream PET operator scheduling strategy, to improve the serving throughput further. Finally, we evaluated the PETS against 2 traditional sequential serving and parallel serving frameworks on 3 different platforms. Compared to the baselines, PETS can support more concurrent tasks and has a higher serving throughput. PETS is planned to be integrated to an open-source inference serving framework, HIE, which is developed by Alibaba. PETS will also support more PET models trained by existing PET training frameworks, such as AdaptHub and OpenDelta. Thank you for your listening. Any questions are welcome.